Hello students, welcome to Educate. Today we are going to study the chapter Oscillations. So here we must know the basic equations and the conditions. So let's see one by one. So the basic concepts that you have already studied like time period, frequency, you know what is time period, what is frequency, what is wavelength. So these terms you have already studied. So here we will see some specific equations and related numericals. The here the very basic thing, that is frequency, is given. Frequency equal to 1 upon time period, and its unit is hertz, abbreviated as hz. Keep in mind, when you write full spelling hertz, then here H should be in small letter, whereas when you use abbreviation, in that case H must be in capital letter. So here there is one question for you. Question says, on an average, a human heart is found to beat 75 times in a minute. Calculate its frequency and period. So it's very simple. Number of beats is given 75 and time is given as 1 minute, and minute must be converted into seconds. So 75 divided by 60 are 1.25 per second, and you know per second is equivalent to hertz, so you can say 1.25. And if you want to find out time period, so just reverse it. So 1 upon 1.25, so this will become 0.8 seconds. And next point is displacement. You understand what displacement is. So suppose you consider the case of simple pendulum. So it is its mean position. So suppose it is here. So this is displacement. Similarly, it will go in this direction. So this will be displacement, right? And this maximum displacement is called amplitude, right? So here we will consider the basic relation, then we will find the condition for velocity and acceleration, and then we will write the relation for time period, etc. So if we take simple relation, like suppose we write y, which is displacement, as a sine omega t, right? Here omega is equal to 2 pi by time period, or 2 pi nu also we can write, because 1 upon t equal to nu. And here time period will be t, means this is like this. After time period t, the wave will be repeated, correct? So we can find velocity. So if we differentiate it with respect to time, dy by dt, it will give a omega cos omega t, right? So this is equal to v. Here we can evaluate like cos omega t. Here this is velocity, so we can replace from here, this is y upon a equal to sine omega t. So what do we get? We will get a omega, and here cos omega t can be replaced by using the triangle. This is omega t, here sine omega t, y upon a. Y is perpendicular, a is hypotenuse, so this will become a square minus y square. So here we can write cos omega t. Cos omega t means base a square minus y square divided by a. So a will cancel out, and we will be left with omega times root of a square minus y square. This is velocity. Now to get maximum velocity, either we can put it as 0, so we will get a omega, or we can say in that case displacement this y will become 0. So same result we will get. So we will get omega times A, and which is V maximum. Keep in mind, if you want to find out whether given equation represents periodic motion, in that case there must be sine or cosine relationship. Like here in this example, if you observe carefully, there are certain cases. First case, you have to check whether this represents periodic motion sine omega t plus cos omega t. This equation can be reduced in terms of sine omega t. Final relation comes out to be like this: root 2 sine omega and then t plus 2 pi by omega plus pi by 4. So hence this will be a periodic function, right? But in this case, here what is happening? Sine omega t cos 2 omega t sine 4 omega t. So although there is, this is periodic, this is periodic, this is periodic, so you have to find out what is common period, and then you can easily evaluate. So the basic point is that sine and cosine functions are used for representing periodic functions. Then comes e power minus omega t, that can never be periodic. Similarly, log omega t can never be periodic, right? Then we see what is simple harmonic motion. So here, here this particle is vibrating hence and forth motion between limits minus a and plus a. So this will be simple harmonic. Generally, the equation should be of the form like either cosine or sine function. All right. So this is basic point. Now let's see next concept. Here different type of waves are shown and that are periodic with the different periods, so that you can understand because they form the basics. Here another question is given, like which of the following functions represent simple harmonic motion, periodic but not simple harmonic? Give the period for each case. So you can easily evaluate sine omega t minus cos omega t. You can use concept here. You can just write cos omega t sine pi by 2 minus omega t, then simplify and you will get a relation, and then you can find its phase angle. Similarly, there is another case which can't be periodic, right? Then some basic properties of periodic functions we can study, like displacement is directly proportional to acceleration, and then we can study different type of graphs, etc. So here we are not going to analyze every aspect. We will see some simple relations, like here this is given: a body oscillates with a simple harmonic motion according to the relation x equal to 5 cos 2 pi t plus pi by 4 at t equal to 1.5 second. You have to calculate what is displacement, what is speed, what is acceleration. So as I told you, if you start from cosine function, two possibilities are there. If we say, if we take y equal to a sine omega t, and here if we evaluate velocity, so velocity will be dy by dt, that will be a omega cos omega t, and acceleration a will be second derivative of this d2y by dt2, that will be minus a omega square sine omega t. So these are the basic equations to find velocity and acceleration. They can be maximized or minimized as per our requirement. If some angle is given, suppose here phi is given, so this will also become phi and this will also become phi, and we can do the evaluation accordingly. Here this is equation in terms of sine function. Suppose we start with the cosine function, a cos omega t plus phi. Then again we can evaluate. So here dy by dt will give minus a omega sine omega t plus phi, and d2 by dt2 will give minus a omega square cos omega t plus phi. So any one equation can be taken and then comparison can be easily made. So here in this question, what is given? A body oscillates with a simple harmonic motion according to the equation x equal to 5 cos 2 pi t plus pi by 4. So here omega t plus phi 0 is given, omega is 2 pi, that is t will be 1 second, and then we can easily calculate. So when t equal to 1 second we write here, so this will become 3 pi plus pi by 4, and then we can put the values. So on putting the values, so this is 5 cos, this 3 pi plus pi by 4. After evaluation, we will get the value minus 3.535 meter. Correct? Then we consider its second part. Here, in second part, we have to write the equation for speed. As I told you, you have to differentiate it. When we differentiate, we get here omega in the back, and then everything you can put. So 5 times 2 pi into sine this. After putting the values, we will get velocity as 22 meter per second. Similarly, acceleration we can double differentiate, and after putting the values we will get 140 meter per second square. Now we have to find out the relation for time period. So general equation f equal to kx, you know, and also f equal to ma, right? And here one more thing we have seen, if you remember, that a is equal to how much? We have started y equal to a sine omega t dy by dt gives a omega cos omega t, and then d2 by dt2 gives minus a omega square, then again sine omega t, and a sine omega t is y itself, so minus omega square y. So acceleration you are getting as minus omega square y, or in terms of x also you can write, here you have taken it. So you can say you have to take this negative, so minus kx must be equal to ma. So here also m omega square x. So from here what do you get? This should be negative, so we can get omega square equal to k upon m, and you know omega equal to 2 pi by t, right? So we can write 2 pi by t here, omega. So let's delete some portions so that thing will become clear. So we have got omega square equal to k upon m, or you can write m upon k equal to this 1 upon omega square. Why I am writing? Because this is just 2 pi by t whole square. Either you write this is k upon m, or 2 pi upon t equal to root k upon m, or, and then you can invert it. So t will be equal to how much? So from here it is clear, t you can take here, so 2 pi root m upon k. So this is the relation. Here same thing they have given, so you can easily understand. And one thing is notable when we write the relation for f, like f equal to minus kx, here negative sign indicates that restoring force is opposite to the displacement. Like suppose this is mean position, particle is here, so there will be restoring force in this direction, and this is displacement. So displacement and restoring force both are against, so that is why we use negative sign. Now up to here I think thing is clear. Now let's proceed. We consider the motion of spring. Here there is one mass, and this is one spring, this is another spring. So if you pull it in this side, so this spring will get compressed and this will get stretched. And if you do the reverse, same will happen. So in this case, the force constant will get doubled. So here our relation of time period will become T equal to 2 pi root m upon, in place of k, both k must be added, so we will get 2k. So this is the case that they have discussed here. Now we are going to see the different types of energies associated with simple harmonic motion. So here what we have to observe, that what is kinetic energy, what is potential energy, what is total energy, and then the graph. So let's see. Since we take y equal to a sine omega t, right? From here we can get velocity, that is dy by dt, which is equal to a omega cos omega t, correct? Now, if we find kinetic energy, or further, we can replace it in terms of sine. So this will become, from here, this is perpendicular is y, this is a, so this is root of a square minus y square. So if you write this value over here, what do you get? You will get omega times root of a square minus y square, correct? And now we can find kinetic energy. So kinetic energy is half mv square, that is 1 by 2 m into omega square into a square minus y square. So this is expression for kinetic energy. Now we can find potential energy. So from formula F equal to minus kx, and also you have studied half kx square. So that formula we can use, half kx square, and x here, x or y, you can take any one, k y square. So after putting values, we will get same relation, 1 by 2, in place of x we can write here y. So 1 by 2 m omega square times y square, right? Because k will be, if you remember, omega square equal to k upon m. So from there, k equal to m omega square. Now we have to find out what is total energy. So total energy will be sum of potential energy and kinetic energy. So after putting values, you will observe that this term 1 by 2 m omega square y square will cancel out. So you will be left with 1 by 2 m omega square and a square. If you wish to write omega is 2 pi times frequency, so you can further write it as 1 by 2 m into 4 pi square nu square a square. So this is total energy. Now if we wish to plot the graph, so graph will look like, suppose we say that here we are taking this, this is total energy, this is mean position, right? X equal to 0, here x equal to maximum displacement, here x equal to negative maximum displacement. We are considering the case of simple pendulum, suppose. So here at this point, what happens? Kinetic energy will be 0, but potential energy will be maximum. So at the same point, it will, graph will be like this. So whenever P becomes maximum, in that case K becomes minimum, and vice versa. At this point, at mean position, P becomes 0, then Ke will become maximum, and at extremities what you observe, that P is maximum and K is minimum, right? So total energy in each case remains conserved or constant. Now here there is one question you can observe. A block whose mass is 1 kg is fastened to a spring. The spring has a spring constant of 50 Newton per meter. The block is pulled to a distance of x equal to 10 centimeter from its equilibrium position at x equal to 0 on a frictionless surface from rest at t equal to 0. Calculate the kinetic potential and total energies of the block when it is 5 centimeter away from the mean position. So first of all, you have to find out its velocity, and then we can calculate. So we have already studied that omega equal to k upon m, because omega square equal to k upon m. Here in our question, k is given. K is given as 50 Newton per meter. So we can put the value, and m is given as 1 kg. So after putting the value, we can get omega, right? And then we can write displacement equation in terms of cos theta. So we can write x equal to 0.1 cos here omega t. Omega has this much value, 7.07 into t. Now when particle is 5 centimeter away, so it means in place of x we can write 5 centimeter. So we get this relation, we can divide it by 0.1, and then we can find the value of t. So let's see. So it becomes cos 7.070 equal to 0.5, or cos 7.070 equal to root 3 by 2, and that comes out to be 0.866. Then velocity of the particle we can evaluate at x equal to 5 centimeter by putting this value, right? So this value, I think you have understood. If cos theta is 0.5, then sin theta we can easily evaluate by using perpendicular upon hypotenuse. Perpendicular upon, here base upon hypotenuse is given. You can evaluate perpendicular and then write this relation. So you will get sin 7.07t equal to 0.866, and then velocity equation you have already got. So you can put this value over here to get velocity as 0.61 meter per second. This is important question. Now to get kinetic energy, you have to apply formula 1 by 2 mv square. 1 by 2 m is given 1 kg, and velocity you have got this much. So you can put this value over here. So after evaluation, you will get 0.19 joule. Then potential energy of the block, half kx square. Displacement is given as 0.05 meter, and spring constant is already given. So you can put the value to get 0.0625 joule. And if you wish to find out total energy, so obviously x equal to 5 centimeter, and you can write x equal to 5 centimeter, you can find total energy. And then here some more information given. We also know that the maximum maximum displacement kinetic energy is 0, and hence the total energy of the system is equal to the potential energy. Therefore, the total energy of the system will be this much, right? So you have understood. Now we are going to see the case of simple pendulum. So simple pendulum, you know basics, how to do. So this is simple pendulum. There is bob, this is thread, this is bob, and suppose we consider displaced position. So this distance is say x. Here there will be one force mg sine theta, which will act like a restoring force, and its weight mg will act downward in this direction. It will be mg cos theta, right? And then we do certain assumptions that when theta is small, then sine theta becomes theta. So this is length L, this is X. That we can write restoring force F equal to, here it is mg sine theta, right? So it should be negative. Why? Because this is restoring force and it acts against the displacement. So we can write minus sign minus mg, and we make certain assumptions. When theta is small, then sine theta will be perpendicular upon hypotenuse. We write it as x upon L, or minus mg x upon L, right? This is F. And also, if you remember, F equal to, what is formula from displacement equation, do you remember? So that is omega square x. So that was m omega square x, right, with a negative sign. So the two must be equal. So if we equate the two, so we can say m omega square must be equal to mg upon L. M will cancel out. 2 pi by t whole square is equal to g upon L. From here, we can write t equal to 2 pi root L upon g, which is very famous equation. This is not 8, this is g, right? So I think you have understood. The same thing is explained here. So this is final relation. Here, there is one important question. What is the length of a simple pendulum which ticks seconds? Ticks seconds means seconds pendulum. We are talking about its time period will be 2 seconds. Formula is T equal to 2 pi root L upon G. Right. So here our concern is to find the length, so we can square it. So t square equal to 4 pi square L upon g, or L equal to gt square divided by 4 pi square. And then we put t equal to 2 second, g equal to 9.8 meter per second square, and time period is 2 second. So sorry, I repeated it. So L is equal to 9.8 into 4 divided by 4 pi square. If we evaluate it, it will come out to be 1 meter. This is one important question. Now let's see next thing. So chapter is over. Let's have a quick recap about the chapter. The motion that repeats itself is called periodic motion. The period t is the time required for one complete oscillation or cycle. It is related to the frequency nu by t equal to 1 upon nu. The frequency nu of the periodic or oscillatory motion is the number of oscillations per unit time. In SI unit, it is measured in hertz. So 1 hertz equal to, we can write 1 Hz equal to 1 oscillation per second, that is 1 second minus 1. Now, another thing is there, in simple harmonic motion, the displacement x of a particle from its equilibrium position is given by x equal to a cos omega t plus phi. Here x is function of time, that is why it is written inside the bracket. This is displacement equation, in which a is the amplitude of the displacement, the quantity this is phase of the motion, and phi the phase constant. The angular frequency omega is related to period and frequency of the motion, that you know very well. Omega is 2 pi by t, or 2 pi nu. Then comes a simple harmonic motion, can also be viewed as the projection of uniform circular motion on the diameter of the circle in which the latter motion occurs. That you will understand. The particle velocity and the acceleration during SHM as a function of time are given by Vt. If we differentiate this equation, we will get minus omega a sine omega t plus phi, which is velocity. This can be maximized or minimized. Similarly, acceleration will become minus omega square a cos omega t plus phi, or minus omega square x, because a cos omega t is x itself. I think up to here you have understood. Here, if you want to find out maximum value, then this will become 1. Here, if you want to find out maximum value, then again this will become 1. The force acting in a simple harmonic motion is proportional to the displacement. This is necessary condition that you have to understand and is always directed towards the center of the motion. Now, a particle executing simple harmonic motion has at any time kinetic energy k equal to half mv square and potential energy u equal to half kx square. If no friction is present, the mechanical energy of the system E equal to k plus u always remains constant, even though k and u change with time. Then comes a particle of mass m oscillating under the influence of Hooke's law, restoring force given by F equal to minus k exhibits a simple harmonic motion with omega equal to k upon m. Here it is angular frequency, T is 2 pi root m upon k, and such a system is also called a linear oscillator. About this type of oscillator we will study in higher classes. Then the motion of simple pendulum swinging through small angles is approximately simple harmonic. The period of oscillation is given by T equal to 2 pi root L upon G. Now some more important facts are given here. Period, symbol T, dimension T, unit S, least time per motion to repeat itself, frequency nu or F or T inverse, and then angular frequency omega, that is its dimension is T power minus 1 and it's given by 2 pi nu. Then phase constant phi, this is dimensionless, and the force constant K that you have studied about basics of force constant. If you remember, we consider a spring like this and we apply some force on it, and suppose spring gets elongated by a distance say x, right? So we write F proportional to minus F proportional to x, and then we write F equal to minus kx. We say that restoring force acts opposite to the displacement, and here k is called a spring constant, right? So here same thing is explained. Then comes another point, you can read it. The period t is least time after which motion repeats itself. Thus motion repeats itself after nt, where n is an integer. That every periodic motion is not simple harmonic motion. Only that periodic motion governed by the force law like F equal to minus kx is simple harmonic. Circular motion can arise due to an inverse square law force, as in the planetary motion, as well as due to simple harmonic force in 2 dimensions equal to minus m omega square r centimeter force. In the latter case, the phase of motion into perpendicular direction section y must differ by pi by 2, of course. Thus, for example, a particle subject to a force minus m omega square r with initial phase 0 and a, here this amplitude and velocity omega a 0, will move uniformly in circle of radius a. For linear simple harmonic motion with a given omega, the initial conditions are necessary and sufficient to determine the motion completely. The initial conditions may be initial position and initial velocity, amplitude and phase, or energy and phase. And from this point, it is given, from this point, given amplitude or energy, phase of motion is determined by the initial position or initial velocity. And then a combination of two simple harmonic motions with arbitrary amplitudes and phases is not necessarily periodic. It is periodic only if frequency of one motion is an integral multiple of the other's frequency. However, a periodic motion can always be expressed as a sum of infinite number of harmonic motions with appropriate amplitudes. Then next point is the period of simple harmonic motion does not depend on amplitude or energy or the phase constant. With this, the periods of planetary orbits under gravitation, Kepler's law, that we have. This is contrast to that. And then the motion of a simple pendulum is simple harmonic for small angular displacement. For motion of particle To be simple harmonic, its displacement x must be expressible in either of the following form, or a here x equal to a cos omega t plus b sin omega t, or x equal to a cos omega t plus alpha, where x can be written as b sin omega t plus beta. So the three forms are completely equivalent. Any one can be expressed in terms of any other two. So we will see later on this thing. And then there is damped simple harmonic motion, which is not strictly simple harmonic. It is approximately so only for time intervals such as less than 2m upon b, where b is the damping constant. So about this damping constant you will study in competition section. So this is how lesson is over. Now we will see numericals in next lecture. Thank you for watching. Team Educate.